A few months ago, I released a video where I was exposing these free energy scams we keep seeing on YouTube. These scams come in hundreds of different flavors, but the most common one seems to be connecting an alternator to a motor, and the idea being that the motor will spin the alternator powers the motor, and you create an infinite loop of energy, so much so that you can tap into that energy and power other devices. Thus, you've got free energy. Some of them even go through the painstaking effort of pretending to modify the alternator. You know, they'll cut the thing open, gut the wires, glue on neodymium magnets with epoxy, and make it appear like they've invented something new. When in reality, it would be better to just buy a synchronous AC motor because in theory, that's what you've just made. Secondly, even if it did work, this is a dumb idea. Electromagnets will always be more powerful than permanent magnets, even neodymium magnets. You've just made a worse alternator, not a better one. But also I know they're faking this because the thing should be vibrating around the table like a giant vibrating toothbrush, yet it's just as quiet as a regular machined alternator. Motor manufacturers go through painstaking efforts to add little weights and balance out their motors so that they don't vibrate and they're quiet. Since we don't hear any noise coming from these things, we can be pretty sure it's been faked. We're looking at the original alternator, not a modified one. In that same video, I brought up the example of trying to add an alternator to an electric car. The basic premise is this. In an electric car, the battery powers the electric motor. And once the car starts moving, you got all this kinetic energy from the car. So what if you connected an alternator to your battery, which was being powered by the drive shaft, the wheels, whatever, and then that energy would be sent back to the battery. You'd create an infinite loop of energy. You could drive forever without having to charge your car. Some people say, okay, well, maybe you can't drive forever, but you would at least extend the range. That's the premise. This idea doesn't work. That's why Ford, Tesla, Toyota, nobody who makes an electric car adds a car alternator. I got a huge pushback in the comment section, well over 10,000 comments, people saying things like, wait, Jeremy, what if you added a capacitor to the system? Or what if you added a transformer to step up the voltage? Or what about flywheels? What about using different size pulleys? What if you used a giant alternator and a tiny motor driving the giant alternator? On and on and on. As I was reading these comments, I realized that there's a common theme. And when students have good questions, every teacher gets excited. And I am sufficiently excited. So I went out, I bought a car alternator, and we're going to power this guy up. I'll show you how it really works. And by the end of this video, you should understand why nobody, Ford, Tesla, Toyota, nobody who makes an electric car will put a car alternator in it, because at the end of the day, it wastes more energy than it adds. And I'll prove that to you here in just a little bit. Before we get started, there's one question I want you to think about. This is a bar magnet, and here we have a wrench. My question is simply this. Is this bar magnet doing work on the wrench? Or put another way, is the bar magnet expending energy in order to hold up this wrench? By the end of this video, you'll understand the answer to that question. All right, let's get started. Okay, I've got a really fun demo that I want to show you with these cups here in just a minute. But before we get into that, I need to make sure you understand what power is, and we're also going to use gears as an example of how power is exchanged from one form to another. I've talked about this extensively in 2 previous videos, but you don't need to watch those videos in order to follow here. I'm just going to cut out 2 little snippets, one from each video, and play them for you right now. It doesn't matter if you're buying a motor off the shelf or you've pulled a motor out of an old broken appliance. Somewhere on that motor is going to be a power rating. And that number is really important because it tells you how much work the motor can do, and it tells you how quickly the motor can do the work. To illustrate this, I've subpoenaed my kids to move some bricks for me. To calculate the power output of my kids, we need to know 3 things. How much force they're applying to the bricks, how far they move the bricks, and how long it took for them to move the bricks. Put all those numbers in the formula and you get power. In this case, if I'm not satisfied with the power output, I can always input some motivation to get better results. Good stuff. Yes, yes. So we just learned that if we move an object a certain distance and we calculate how long that took, we know how much power is required in order to move that object. We also learned that if the distance moved is 0, the power output is 0. So if we go back to our magnet example, we can see that the power output of this magnet is 0. There's a force being applied, but there's 0 distance, which makes the power output 0. Okay, so let's think back to my kids carrying the bricks for a moment. No matter how much I feed them or how much external motivation I try to give them, they have a limited amount of power that they can put out in any one given time. But if I lighten the bricks, they could potentially run faster, or I could make the bricks heavier and allow them to go slower, giving me the same power output. And this is where gears and pulleys become really important. In order to illustrate this, I built the most ghetto seesaw you've ever seen, and I talked about this in a previous video. So let's take a look at that. If you've ever been on a seesaw, then you know what it's like to sit opposite of someone who doesn't weigh the same amount that you do. You intuitively shift your body weight forward and back to try to balance out your weights. What you're actually doing is balancing out the torques. Torque is a combination of the force being applied to the lever times the distance from the center of rotation. In this example, you can see my kids quickly figured out that if you have twice as many bricks, then the lever needs to be about half as long. The same thing is true with any sort of lever. And now I want you to think about each tooth on the gear as being an individual lever. Since the motor connected to this gear has a fixed amount of torque, increasing the length of the lever means you decrease the amount of force that can be applied at the end in order to balance the equation. The same thing is true for all forms of mechanical advantage, including pulleys. Looking at this pulley, for example, the center of rotation to the groove is the length of our lever. The motor itself has a fixed amount of torque. Therefore, in this case, we take the motor's torque divided by the length of our lever, and that's how much force we can apply to the belt. So let me give you a pop quiz. If we put this pulley on the motor instead of this pulley, what do you think is going to happen? Hopefully you're saying to yourself, you should get way more force output on the belt for this one than this one. And you will be correct. The force that you can apply on this pulley with the same motor is going to be way higher. But there's an interesting trade-off. If you look at the arc length from here to here compared to this one, it's way longer, right? To go a half a rotation on this pulley means the belt will have moved significantly further than with this one. And that's actually the trade-off that you get. Putting this guy on your motor is going to give you much less force, but a great deal more speed. And vice versa for this one. You can put out a lot more force from your motor, but it's going to be a much slower speed. All forms of mechanical advantage have the same secret sauce. Whether you're using gears, pulleys, a block and tackle, you're using a car jack, hydraulics, they all work exactly the same way. The total amount of work being done is always the same. But if you use mechanical advantage, you can get more or less force output by trading how much distance you actually move. Hopefully this will distill one of the very common myths that I run into, where people think that you can just take pulleys or gears and increase the work output. That's not what these things do. There's something being given up with each one of these exchanges. Now that we see them side by side, hopefully you can start to see the parallels. The major difference between these two is these will both spin in the same direction and these will spin in opposite directions. If this is our driven gear, then one full rotation will not produce one full rotation here, and therefore the output speed is lower. But again, the torque is higher because the length of the lever arm is longer. The same thing is true over here. One full rotation of this pulley means however much belt will go around one full rotation is the same amount that will go around this, and therefore we won't get a full rotation on the output. Lower RPM, but higher torque. Let's make one solid example so you really have this fixed in your mind. We have a go-kart. It can carry 100 pounds and drive at 20 miles per hour. You can make those units whatever you like. This could be 100 kilograms and kilometers per hour. Whatever makes you feel good. The key here is gears allow you to trade one for the other. So we can lower our carrying capacity if we want to increase our speed. And this would very likely be feasible with gears. You could cut your towing capacity in half and double your speed. The same works vice versa. We could cut our speed in half and double our towing capacity. But what you cannot do is leave the capacity the same and try to increase the speed with gears. This won't work because you need more power in order to increase the total amount of torque and speed combined. That's the definition of power actually, is speed times torque. Now, we can certainly get the wheels to spin at 40 miles per hour as long as the load is below 50 pounds. But if you try to carry the full 100 pounds, you're not gonna get this go-kart to spin. In fact, it's just gonna stop dead because there simply isn't enough power available. This kind of system would require a larger motor because you need more power. If you took that same go-kart and you lifted up the back wheels, there's no load on these wheels, they will definitely spin at 40 miles per hour. But as soon as that go-kart touches the ground, it's dead in the water, it's not gonna move. This is the trade-off that you're always gonna experience with gears. They don't give you more power, They just allow you to trade speed for torque. Okay, I have a series of cups here which represent different mechanical devices that you all have recommended we use in order to increase the power output. Spoiler alert, none of these increase the power output, but I'll explain that in just a moment. Let's start with an electric motor. Motors convert electrical energy, electrical power, into mechanical power. So we're gonna add some power because no perpetual motion machine will work if you don't start it. So we need some initial input power. We want to transfer this from our motor to our alternator. So we're gonna use gears. We can either increase the speed and decrease the torque, which gives us the same power, or we can increase the torque and decrease the speed. But guess what? The power output is exactly the same. So we're gonna transfer this over. We haven't gained any power, we've just transferred the power. Now we need to move that over to our alternator. Here's our alternator. And there we go. But for our perpetual motion machine to work, we need to cut this in, we need to put this into a loop. We need to send this electricity back to the motor. But there's a problem. In real life, the transfer is never perfect. There's always some wasted energy every single time. So we've got resistance in our wires, we've got friction, all kinds of things that produce resistance and makes you waste some of the power. Motors back to the gearbox. There's also friction and heat, your gears will waste some power. We want to add a flywheel. Well, you're converting some of that energy into kinetic energy spinning the flywheel, but you've got to accelerate and decelerate the flywheel, more energy wasted. I hope you're starting to see the point here. If we want to send this to a transformer, transformers convert voltage into current or current into voltage, but the power output is exactly the same. So we want to dump some of that into a transformer. We're just wasting power with each device we add. Another idea that several people suggested was, what if you use a really small motor? Let's dump this back into the motor. And you have a giant alternator, right? It's the same problem. You're transferring the same amount of power. It doesn't matter how big the system is. You can only get out of it the power you put into it, right? That's all you get. It does not create additional power. Even if we add multiple batteries, which was one that a lot of people suggested. We have a battery here. We're going to dump some power in our battery. And as you can see, we're going to eventually run out of power. If you want to split this across multiple batteries, each one converting that electrical energy into chemical energy and then back, each transaction is wasting power. That's the take-home message. Every time you transfer, you waste some power. Pick any device you want. You want the kinetic energy of the car. Some of you said, well, the car is already rolling. What if you attach the alternator to the wheels? Well, guess what? The alternator requires mechanical energy in order to rotate the shaft. So when you dump power from the car's kinetic energy back into the alternator, what you end up with is a braking effect because the alternator is going to resist turning in order to transfer that power. Essentially, you're riding with your foot on the brake. Here's a good opportunity to talk about something called regenerative braking. Essentially, electric cars will turn the electric motor temporarily into a generator when you want to slow down the car, allowing you to dump some of that energy that you would have wasted as heat on the brake pads. You get to put that back into your battery. It's a small amount, but it does help to extend the range of the car. It's not free energy. You've got kinetic energy from the car. You want to use up some of that kinetic energy. And so you will turn your car's motor into a generator that dumps some power into the batteries, but it also slows the car down. So again, alternators, electric motor used as a generator, doesn't matter which one you use, they are absorbing power from the car. And even that transfer back to the motor is going to waste some power. Okay, so I've got one more example I want to show you, and that is when you spin the alternator, it requires force to spin the alternator. It doesn't just free spin. Exactly the same way that it acts like a brake on your car if you try to draw power out of it while the car is rolling. It will also act like a brake when I try to spin it if I have a power source connected to the alternator. And I'll show you that right now. Okay, I've got a stupid simple test that's going to show you how all this works. So here we've got a power meter, and electric motors have this amazing property. They only draw enough power to match their output. So if there's no load, if I remove this belt, then what we should see on this motor is exactly the amount of power it takes just to keep this shaft spinning at the synchronous speed or just below synchronous speed. When I reconnect this belt and not have anything powered on the alternator, we'll be able to see the difference between the two. In other words, we'll see how much power it takes just to spin the alternator by just doing some simple subtraction. Then we'll plug some things into the alternator and you'll really start to see how perpetual motion is impossible because every component in the system is using up some of the available power. Let's start by just running the motor and seeing how much power it takes to run the motor. Let's go. Okay, I think it's safe to say that's about 262 watts. Let's throw the belt back on. And now we can see how much power is required to run the alternator. Okay, I'm gonna put a little more tension on this belt and then we'll get going. All right, we're ready for step 2. We've got 12 volts on our alternator, which is what you need in order for the alternator to work. Normally in a car, it would just be the battery connected back. In this case, I've got a 12 volt power supply. So the alternator is wired the way it would be in a car, with the exception of there's no load on the alternator. It's not powering anything, okay? So let's see what it takes just to free spin the alternator. We should be able to figure that out by subtracting the total power used from the power that this uses by itself, which was 260 something watts. Okay, it seems to be holding pretty steady at 994. So let's try plugging something in. And we can see the light bulbs adding just a couple of watts. Unplug it, and you can see it going back down. Okay, hopefully the message is clear. Alternators require power to spin them. There's a base amount of power just to make the thing free spin. And if you want to plug something else in, that's going to require some additional power. So attaching it to your car doesn't just suddenly give you free energy. You're going to have to provide some additional power from the motor in order to overcome that braking force. In the same way that you can drive with your foot on the brake, the same is true with an alternator. If you add an alternator to an electric car, it will be able to drive, but the electric motor is going to have to work harder in exact proportion to the amount of power being required by the alternator. And because it's not just charging the battery, but also wasting a little bit of power in the process, no car manufacturer will do that because you're going to lower the overall mileage of the car, not extend it. Now, some of you have such a powerful hope that this is true. The temptation of free energy is so great, you're going to walk away saying, you know what, I don't care what he says, I think it's still possible. And to you, my brother, I say, more power to you, man. Spend the rest of your life working on this if it brings you joy. I'm going to teach my kids about the laws of physics because at the end of the day, when you understand where the boundaries are, you can operate and think so much faster, pushing right up to that edge, even testing those boundaries. But when they prove to be real, you don't spend the rest of your life banging your head against a brick wall. So let's get back to the vast majority of you science-loving folks who just want to know if these devices are real or not. Well, we've been skirting around one of the fundamental laws of physics, and that is energy can't be created or destroyed. It can only be transformed. Its form can be changed, but you can't increase it or decrease it. You just change its form. This is a law of science because there are no known exceptions. The same way that we learned that gears don't increase power output, they simply exchange speed for torque, transformers exchange voltage for current, and all of these other devices that we mentioned, each one of them has a unique way of transforming the way power is either stored or used, but none of them can multiply the output. None of them make an over-unity machine more likely. None of them make a perpetual motion machine more likely. There is also no arrangement of devices which could possibly multiply the output, because just like the cup example I showed you earlier, every device you add is wasting a little bit of energy. And it is absolutely impossible to spill power all along the way through the system and somehow end up with more, and therefore you cannot arrange devices in a way to get more power out than what came in. I don't think I can make it any more plain than that. The best part about science and engineering is that it is measurable, repeatable. If you want to do the experiments I did today, there is nothing special about this setup. You can get this alternator at any local auto parts store. In fact, try different sizes, get one for a big tractor trailer, get a little baby one. I am certain that you can optimize this setup to get more power out of it, a more optimal power setup than what I had. My goal was only to get about 2,500 RPM just to prove to you that it takes power just to spin the alternator. It doesn't free spin, and therefore it's impossible to get free energy because you're wasting energy before you even start to make any. We were also able to measure that at the input, which proves that there's a braking force, that it takes mechanical power in order to get the electrical power out. There is no free energy. The power has to come from somewhere. My little power meter cost about 20 bucks on Amazon. I'll put a link to that in the description. All of this stuff is easy to copy, and I want it to be easy to copy because I want you to be able to learn this stuff for yourself. You don't have to take my word for it. I hope you learned something great today. If you're interested in learning more about science and engineering, that's what my whole channel is about. So I encourage you to hit the like and subscribe button and also click that little notification bell if you want to be notified when the new videos come out. Thank you so much to my patrons who are scrolling on the screen over here. These fine people are the ones who help me make this kind of content possible. Anyway, thank you so much for watching.